Welcome back, everyone. It's a pleasure to welcome Emily to the family of Multicore World because she's a newbie. So hopefully it's the first of many times. So from Los Alamos, you are probably the fifth Los Alamos person in Multicore World. So Emily Casleton, please.
So thank you. Thank you so much for inviting me to be here today. I really appreciate my first time being in New Zealand. So I will say I was a little nervous being a statistician presenting at a computer science workshop. But with AI, I feel like this kind of binds us all together, or maybe ties us all together as we sync together. So I threw this in yesterday, this About Me slide that I feel like other people have added in as an introduction. So high level about me, I'm a statistician and I like being outdoors. Bonus points if I get to be outdoors, and it's also with my kids. I went to Claude and I said, I have a PhD in statistics. What do you think that means about me? And so here's kind of some cherry-picked answers about what Claude thought it meant about me to be a statistician. And specifically, I asked, do you think this makes me cynical because of my PhD in stats? And so what it told me was statistics training leads to some healthy skepticism, ability to question things, and a low tolerance for statistical innumeracy in public discourse. And that this could possibly be perceived as being negative, difficult, pedantic, or pessimistic. I like Ilke's quote this morning, how if you're uncertain, then you don't know, which I can appreciate that being a popular characterization. And apparently some statisticians do become genuinely cynical, which I can relate to, because of the misuse of statistics, cherry-picked data in important decisions, and resistance to evidence. I have often said that I think the world in general would be a better place if the general population had just a basic knowledge of statistics. But thank you. But I think all of this is kind of leading into, I feel like statisticians have a very good role in testing and evaluating AI models. And I think this is a great place for us to be, and so I'm super happy to talk to you about this today. Okay, so a lot of what we hear about AI, a lot of what has gotten a lot of press in AI for a while is the model development, coming out with these big, super big models that can do really, really impressive things. But I feel like testing and evaluation is maybe finally having its moment. In this report from Stanford, this report talked to AI experts at Stanford and asked kind of what is on the horizon for AI, specifically within the next year. So this comes from the summary of that report, and my favorite quote, the era of AI evangelism is giving way to an era of AI evaluation. Further proof of this, there's this National Academies of Science report that came out, and this is kind of, again, the overall summary, and the point that I highlighted here. The rapid adoption has raised questions and concerns about the reliability, validity, and reproducibility of these models. So again, I think it's finally being recognized that testing and evaluating of these models does need some more effort. However, so I work for Los Alamos National Lab, which is a national lab of the Department of Energy. I really thought that I would have to kind of explain what the Department of Energy was. I didn't realize that half of the audience would be employed by the Department of Energy. But so the needs for testing and evaluation for this agency is a little unique to what we see in the commercial sector. So again, from this National Academies report, they talk about how these models that were developed for the commercial industry struggle to transfer directly to what the DOE needs are. And the reason for this is their science workflows. We need these physical consistencies. So as Karen mentioned before, the preservation of mass, energy, and momentum. These are things that we need to take into consideration for the mission needs of the Department of Energy. And the report goes on to say that the way that we can address this is with physically informed architectures and domain-specific verification, validation, and uncertainty quantification methods. So I really kind of like to set the stage with this framing of talking about what is evaluation. So what are we doing when we're evaluating these models? And I'd like to frame it as the core aspect of evaluation is actually prediction. And this comes from a really great paper, The Perils and Prospects of Evaluation. So what we're doing when we're evaluating is we're actually predicting if the system is going to be suitable for what we want to use it for. So we're predicting if the system will perform at an acceptable level in the real world, because this is where we're going to actually use these models, on a new task or maybe a task that was already trained to do, and this is on average. So this is, again, just kind of a setting up the stage for this is what we're looking for in evaluation. It's actually a question of prediction. So in terms of that, I feel like the AI field has definitely over-optimized for topping a leaderboard. Whenever a new model comes out or a new iteration of a model comes out, you hear about how it performed on all these top leaderboards. And kind of going back to the, these are different needs for commercial sector versus the Department of Energy. This is kind of in contrast to scientific testing or, having rigor into your scientific, into your evaluation. And so what really happens here is your metric is the mission. So the whole point of the model is to go after whatever metric is. I kind of mentioned this in the panel the other day. Metrics are kind of a big thing for me. So I kind of see there's a couple ways we can kind of get away from this kind of chasing leaderboardism. And I'm going to talk about two examples in particular on some work that we've done on a couple of my projects. And the first one is metrics that actually inform about the scientific question that we want the model to answer. And the other one, that's kind of two parts, is putting some uncertainty value on the metric values, and then also attributing how the model does to kind of the metadata of the benchmark. Okay, so first part of this, I'm going to talk about new metrics for scientific applications. So kind of what we've been developing on this project called Artemis that Nathan will talk about in great detail tomorrow is developing bespoke metrics for more informed results and more efficient training. And this definitely ties in quite a bit to what Karen talked about this morning. When people were building these models, when people were evaluating models, mean squared error or derivatives of mean squared error, like root mean squared error, are always used as the default. There's little thought that's often put into, is this metric actually going to tell me what I want to use the model for? So, MSE is an important thing. We all use it. It's impossible to run a program and not get MSE out. But I guess what I'm advocating for here, and when I'll talk about what we've been doing, is just thinking about what metric it is that you're using. So kind of what we found is, we want to answer the question, is this model appropriately answering the question? But what this requires is very intimate collaboration between the people who are testing the models, the people who are building the models, and then the people who are going to eventually be using these models. So the subject matter experts. The subject matter experts have to be there to define what is success for a model, what does failure look like, what does failure imply, and then the model builders have to be able to incorporate that into the model. Test and evaluation has to be able to quantify if that success is met. And this seems kind of obvious. Just think about what metric you're using. But it is kind of a novel thing in this space, just to put thought towards it and to work closely with the people who will be using models. Okay, so I'm going to talk about two examples of what my team has done with developing new metrics for scientific applications. I will say the models that were built are super cool. They were developed under this Artemis project. They have a lot of really cool features about them. I'm not going to talk about them. The point of this talk is the metrics that are used to evaluate it. But I would encourage you to kind of look into the models that were being developed. So the first model that I'll talk about very briefly is this TELUS FM. And what this model is designed to do is you have a material, and you have some initial pattern of fracture within the material. What the lab has these large-scale simulations that will take this initial configuration of a material and apply a consistent stress on either end of the material. And they do this until the material breaks into two pieces. And so you can imagine that as you're applying these stress, I should have mentioned, these are cracks. These are little cracks within the material. So you can imagine you're applying this stress on either end of the material. Eventually, these cracks will kind of line up. And if they span two edges of the material, then your one material becomes two materials because it breaks in half. So the way the simulation works, and then the way the emulator built to emulate this simulation works is the model takes in this initial configuration, some kind of metadata like what material is it, how much strain and stress is being applied to the model or applied to the material. It goes through, and then the model predicts how long it took for that one material to become two, and then also what the final fracture pattern looks like. Here's some examples of what has been developed on the model development side. So again, it's kind of cool stuff. So you can imagine this, we have two different types of initial configurations of cracks. The ground truth is what comes out of the simulation, and then the predicted is what the model predicted. So you can see, at least in these two very cherry-picked examples, the model is doing pretty well. Okay, so now getting into the metric development. So we have developed a metric called topogeo similarity, and I'll get into kind of the details of it a little bit. But one of the things that we found with using just MSE, all right, so we had this initial fracture pattern. This is what the simulation produced. This is what the model produced. Model was trained with MSE. We evaluated with initially evaluated with MSE. MSE here is pretty small, so we think, oh, it's, did a pretty good job. The problem with MSE is because it's a mean and it's going after kind of the average, what it tends to do is hedge its bets and be very conservative. So you can kind of see in here, it kind of like blurs the lines. It doesn't want to the model tends to not take any risks because it wants to get everything right on average. But what happens with this prediction here, again, nice and cherry-picked, there is no spanning crack. That's the whole point of the simulation. So in this output of the prediction, the material is not going to break in half. So the spanning crack is the most important feature that comes out of the model. And so by using MSE, we don't know when we're capturing that spanning crack. We're not penalized for not capturing that spanning crack. But for the subject matter experts, that's the most important thing, because if you don't have that, again, you don't break into two pieces. Okay. So this topogeo compares, we're looking at that important feature, that spanning crack. And there's a lot of details here that I'm not going to talk about because I don't feel like that's all that important. But what we're doing with this topogeo metric is we're looking at the spanning crack in the target, we're looking at the spanning crack in the prediction, and comparing that. We're using these kind of 4 different ways to compare the two things, and then we just take an overall average of those. And so we compared, what came out of that topogeo similarity to what we got from MSE. This MSE is now looking at the model evaluation as opposed to like the training and the loss. And kind of what we can see here, so topogeo is a similarity metric, MSE is an error metric, and so if they were kind of telling us the same thing, we would expect it to be anti-correlated. It's not what's actually happening. So for a lot of these, the MSE is very low, in particular shale and tungsten here. All of the MSE values are really low. So our evaluation for that would say that the model's doing really well. But if we look at the values of the topogeo, you can see even for you pick a low MSE value, the similarity metric's kind of all over the place. And so this topogeo is able to give us a lot more information about what's actually going on in the simulation, what's actually going on in the model prediction than MSE. Okay. All right, now I'm going to completely switch to a different type of model. This is a model that we've focused quite a lot on the Artemis project. And this is a model that is doing autoregressive rollout. So an autoregressive rollout is a surrogate for a very computationally expensive solver of partial differential equations, like Navier-Stokes equations, for example. So what the model is hoping to do with autoregressive rollout, the model is given an initial state of the simulation, and it's told to kind of emulate what the simulation would do. So, we give you time 0, do the rest. Go all the way out towards the end of the simulation. So here in this example here, we have the top row is our true values, and then this is what the model predicted. Again, eyeball norm, you can see it's normed pretty good. So the reason that we even want to do this, why would we even do this, is computational speed up. Karen talked about how sometimes these simulations can take days or months or weeks, but if we could do this more quickly, then we can explore the parameter space more quickly. We can design things more quickly. There's a lot of advantages to doing something like this. So there's some issues that need to be worked out. So obviously, if you make an error going from time 0, or I guess time 1 to time 2, you're not going to get better as you keep rolling out. These models are very good at memorizing things from the training data, maybe not as well at generalizing. And again, we need a metric that can distinguish performance. And I can't stress enough, a lot of these issues, there's a lot of cool tricks to deal with them. There's a lot of stuff that has been developed under the Artemis project. I'm not gonna talk about any of it, but I do just wanna highlight that there's so much cool work going on this project. Okay, so to kind of motivate the metric that was developed, I'm going to give a bit of a toy example here. So this is autoregressive rollout for 20 time steps. We'll say 19, starts at 0. And so what I'm showing here is just the very end of the simulation. So imagine model gets time 0, and it goes all the way out to time 19. So we have our ground truth here. And then we have 3 models. We're calling them tiny, big, and large. These were developed. This is the Poseidon paper here. This is their 3 models that were developed to do autoregressive rollout for this particular data set. So using our eyeballs, we can see that tiny does a pretty terrible job. It's just random noise that it's producing at this point in the simulation. Big, again, does the MSE trick where it just kind of smears everything out. And large, it's not great, but we could probably all look at this and say large is doing the best. Big and tiny are doing pretty terrible. So in this plot here, I'm showing the MSE versus looking at this its average correlation coefficient. Again, there's a lot of details in here that I'm very, very much glossing over. And this red box here is highlighting the last 4 time steps, so those ones that I showed in the previous slide. So looking at MSE, again, big and large seem to be doing pretty similar. But we saw on the previous slide, big wasn't really doing anywhere near as well as large was. And so here, MSE is not really telling us all of what's going on. This kind of complicated-ish correlation coefficient now is showing that there is some difference between how the large model is performing versus tiny and big. So we are able to actually distinguish the performance of those 2 models based on kind of a more intuitive or a more informed metric. So that was kind of so that example that I showed was for just one, again, cherry-picked example. We did this we kind of took that correlation coefficient idea and then mapped it into 3 different metrics, and then did it on a whole suite of simulations. And again, this is tiny, big, and large. So we have this maximum correlation, zero lag correlation, spatial offset magnitude. Again, I'm not going to go into the details of this other than to say, we work closely with the physicists and the model builders to kind of develop these. And the really nice thing about these 3 metrics, when we take them together, we can actually say something about the models. And if the models are, getting the physics right, by comparing this row max versus row not. If they're both pretty close to 1, then we say we're doing a really good job. We can, if our row max is less than 0.9, but this spatial offset is small, then we have an idea of what's going on within the model. It's wrong intensity or dissipation, and how to adjust that. So again, not only can this metric tell us, distinguish between the performance of the different models, it can also kind of provide information for what might be going wrong, or how the model builders can incorporate different things into revising the model. Okay, so next up I'm going to talk about uncertainty quantification on metrics. Again, these were just kind of 2 examples of developing metrics that can be used, that are informed by physics and can be a little more informative than MSE. So for uncertainty quantification on metrics, I'm going to motivate this with something a little different. I'm going to use the Visual Task Adaptation Benchmark, or VTAB. So this is a pretty popular computer vision benchmark. So one of the criticisms of machine learning evaluation is this I'll call it disease called leaderboardism, where you choose a model based on it's just a rank of models and then a list of their accuracy. No three numbers for the top 3 models, even though it's summarizing millions and trillions of parameters. So what I'm going to show here is, so we have this VTAB benchmark. Again, this is just kind of a popular benchmark that exists. Within the VTAB benchmark, there are 3 types of images. So there's the natural images, so things you would take with your camera. Specialized images, these are medical images, so looking for tumors or different cells. And then there's these structured images here, and it's almost always just these different objects in a frame arranged in different ways. So you can ask the model how many blue boxes are there, things like that. So this benchmark, again, is used to rank a lot of the popular computer vision models. But how the models are ranked on this benchmark is with an unweighted average of the accuracy of how the model does on all 3 of those image types. So what the work that we've done here is, instead of looking at an unweighted average of those 3 image types, let's look at all possible weights that could be applied to those different image types. So that's what's shown in this plot here. So this is how you read this plot. Each point in here represents a kind of a triplet of those weights that you could put on those 3 different types of images. So the point that's right smack dab in the middle, which is maybe around there, would be the unweighted average. So 0.3, 0.3, 0.3 on all the different image types. So this is a nice way that kind of relates back to how is the model doing based on some metadata of the benchmark. The color in the triangle represents the model that was the best for that combination of weights on the 3 different accuracies. And the gray represents an indeterminate. So what that means is, if the top 2 models were performing statistically equivalent, so we put uncertainty on the accuracy, the average accuracy of the models, if there was no clear winner for that triplet of weights, then the color is gray. So you can see, maybe not surprisingly, that a lot of the triangle is gray. So for most of the, I have plenty of time. So for most of the different combination of weights, there is no clear winner. Again, this is very important because we're chasing this leaderboard, we're trying to get to the top, but there's so much stochasticity and so much uncertainty in these models. But here we're showing that there is no clear winner. The other thing I like to point out in this is this little corner over here. So the way that we read this is if we put all of the weight on these structured images. So let's say you really cared about structured images. That was the main goal that you wanted to use the model for. This corner here represents this rotation matrix. And when we did this work, this was the 6th ranked model on the leaderboard. That's not something you would ever get from just looking at a leaderboard of list of models and the average accuracy. But this way of representing it, we're able to see that that model performs really well on structured images as opposed to all the other ones that are above it on the leaderboard. Okay. So I talked a lot about coming up with new metrics that are informed by physics. So what would be great is if we could get to evaluating models on these physics-informed metrics, but also incorporating these physics-informed metrics into the loss function so that we can better be able to train the models to do what the physics that we want to incorporate into that. However, I'm not advocating for just throwing out all of the machine learning metrics. I think that they definitely have a place as well. So, these traditional machine learning metrics are crucial for state-of-the-art developments. They're definitely necessary. Again, you kind of get them for free anyway when you're building these models. They're automatically spit out of the software. And they're also, so for the physics fidelity, the metrics that are informed by physics are also often very computationally expensive. So being able to incorporate that into the loss function, for these big models, we're just not quite there yet. So at least a lot of the metrics that we have developed, there's a lot that goes into that. Doing that in an optimization loop just isn't possible at the moment. So I feel like, I think Karen also said something about like bridging the gap between machine learning and physics informed. So that's kind of what this picture represents here. So, there's good machine learning metrics, there's good physics informed metrics. We need both to be able to get to new science. And then maybe we can get to a point where we have a machine learning metric and physics informed metric that kind of gets in between both of those two axes. So yeah, there's a lot of work that's still to be done on testing and evaluation. I feel like this is a very nascent area of machine learning, which is an exciting place to be. So what I hope for the future of evaluation, again, more emphasis on defining the specified capabilities and holistic evaluations. So I know I said a lot of bad things about MSE, or implied a lot of bad things about MSE in this talk, but there's no one best way to evaluate all models, which again, I feel like the point of this talk is mostly just put thought into what metric you're using to evaluate your models. And I think an important question to answer is this model appropriate for my application? And so that involves defining very specifically what your application is and what you intend to use the model for, which I think is an amazing exercise to do anyway. And I really like this figure that I stole from the CDAO, which is in the Department of Defense, how correctness is just the tip of the iceberg. So having a model that's correct is great, and you need that, but there's so much other stuff that goes into when you would use a model, how would you use a model, that should also be considered. I think I'm early, but I'm done.